the reason is that a fully specified electric potential also fully specifies electric field. And this is an illustration of that. So what this question gives you is electric potential as a function of x, y, and z, as a function of the three-dimensional variables. It says in a particular region of space, the electric potential is given by this particular function. What is the electric field in the region? And to get each of these, it's an application of this simple formula that electric field of any particular component is given by minus of the partial derivative of the potential with respect to that particular coordinate variable. Let me write, sorry, that's very unusual notation, x sub I. So this is simple enough. Let me just quickly do the derivative. So the x component of electric field is going to be minus of the partial derivative of the potential with respect to x. Just staring at that expression there, I see the second term goes to 0, so I'm not going to worry about it. First term, it becomes minus 18x yg squared. So it's still going to be a function of y and g. That's fine. That's how it's. Let me do the y component. Oh, wait, minus. So the minus cancels out. Y component is minus the partial derivative of the electric potential with respect to y. So let me do the, both terms have y in it. So the first, and let me just pre-cancel the minus with those. So I'm not going to write that minus. So the first term is going to be plus 9x squared g squared. Second term is going to be plus 2 times 5, 10y. That's the power rule. Finally, the g component is the same formula again, same application. And this is almost mechanical because derivatives are easy. There are analytical expressions for almost and most analytical functions. So so the partial derivative here is 2 times 9, 18, and plus a sign in front because of the two minuses canceling each other. 18 x squared y t. So that's it. Those should be correct expressions. Now, the reason I want you to go through this is to tell you one more useful thing that's maybe more useful in the upper division than here, which is, so for this question, we gave you basically an arbitrary function and told you that this represents the potential in the space. And that was perfectly fine thing to do. That's there's no problem in doing that at all whatsoever. We can just do that. Now, what I will tell you is that you can't always do that with the electric field. At least not without potentially running into problems. I guess if you really want to make it so that this region of space, it doesn't have to be vacuum. It can be just anything. It can, even if it could, even then there are, I think, constraints. So yeah, this is why this is, for now, beyond the scope of this class, is that electric fields, they have constraining equations, particular equations that they have to obey. The one that you learned so far is Gauss's law, which relates to divergence, if you learned enough multivariate calculus. But in our class, it's expressed in this form. It's expressed in terms of the electric flux. There's a constraint on electric flux that relates to charge enclosed. Okay, so maybe you specify any arbitrary function as electric flux, and whatever this flux has to be, that's the charge. Maybe you can do that. That's where you get constrained by the second equation that you will see later in this class, which is called the Faraday's law. So Faraday's law, which you will see later, said it gives you a line integral of electric field. It says line integral of electric field over a closed loop, and in electrostatics, that's always zero. In the context involving Faraday's law, where you're not dealing with electrostatics anymore, this is given by the time derivative of the change in the time derivative is the change. It's given by the rate of change of the magnetic flux, which we'll get to. So if you're dealing with electrostatics, then this is zero in electrostatics, and this becomes a constraining equation. And if you learned enough multivariable calculus, this can be described in terms of a constraining relationship on the curl of this vector field. And specifically, this is the expression you would see. Curl of this particular vector field in electrostatics is equal to zero. And so, specifying electric fields in an arbitrary way, it's a dangerous thing to do. You can run into a lot of trouble for doing that. Specifying electric potential as an arbitrary function, that's perfectly fine, because these constraining relationships on electric fields, they are automatically satisfied for any arbitrary electric potential that you can plug in through, and you can I'll leave this as a mathematical exercise for anyone interested. You can go through the the notations here, go through what it means to apply curl, if you've already finished taking multivariable calculus, and you can see that the electric field being specified in this form necessarily implies that curl is equal to zero. So, so that's a bit outside the scope of this class. It's more of an upper division thing, but I just wanted to highlight that since the opportunity is here.